check. Hello. Today this video will be talking about opportunistic design for additive manufacturing and a design technique known as in-situ embedding. By the end of this video, you should have a general idea of the different types of opportunistic additive manufacturing and the different pros and cons that are associated with them. I will provide a couple pros and cons for each of the different categories, but it is not an exhaustive list, but can be very useful if you consider implementing them in your 3D printed parts. In addition, I will explain what in-situ embedding is and how to design a part that takes advantage of this technique, especially when using additive manufacturing. So to start, I will discuss opportunistic design for additive manufacturing. There are typically four categories that this will mainly pertain to, each being a type of complexity, and each providing different benefits and drawbacks depending on how you implement it. Now, as an example, our first category is material complexity. I have a material jetted part from a Object Connex 350. As you can see, we have two different materials here. The black is actually a slightly flexible rubber, and the cream is a rigid material patterned all the way through using a gyroid. Now, the main benefit here is that we have two material properties within the same volume, where we can have a rigid area on one end and a flexible area on the next. But one of the drawbacks to this is if the materials are not miscible, where they don't mix together when introduced, then you need to take into consideration how these two materials are going to connect at their interfaces. So if two materials are not compatible, it can often lead to weakness at those joints. So yeah, here's an example of material complexity. For our next category, it is going to be referred to as hierarchical complexity. This is often referred to also as scale complexity in dealing with how tiny of a part you can get within the same part that you're trying to print something large. And as an example, I have a SLA printed buck that's stereolithography. Now, from people playing around with it, we have one antler broken off. But we can see the detail on the antler over here that allows us to see how fine of a detail we can get while still maintaining the larger body throughout the rest of the buck. Now, to really emphasize the scale that you can benefit from in hierarchical complexity, I've printed a smaller version from the same file. Now, these were both generated from the same file but just scaled in the slicing program before brought over to the printer. And we can really start to see the detail of each of these antlers and how tiny that can get while still maintaining the detail of the rest of the body. So now the benefit here is that we're able to scale the same file and create different sized and different feature sized parts within the same print. But our con is that this is entirely printer dependent. So if you were to take this same file and bring it to a material extrusion printer, you're going to have very different results than this SLA printer has produced. So our next category is going to be geometric complexity. And for this, I have a material extrusion part that is actually a motor bracket to attach a motor onto a 3D printer extruder. Now, the main thing I want to focus on here are these wavy channels that are passing through, which are designed to actually carry these Teflon tubes. Now, in traditional manufacturing, all holes are straight because drill bits are not curved, and so you have to always drill straight holes. But as you can see here, additive manufacturing allows us to be able to pass a tube all the way through and still follow the track that has been manufactured by the 3D printer. So this type of complexity is not available with traditional manufacturing, and that's its main benefit. But the drawback is that you still need to consider restrictive elements of design for additive manufacturing, like support material, bridging, and overhangs. Otherwise, yeah. So our fourth category is going to be functional complexity. This is dealing mainly with printed assemblies and multi-part assemblies that are printed all at the same time on a 3D printer. For this, I have a material extrusion printed bearing that is entirely functional. Now, this bearing was printed all at the same time, and as it was pulled off the bed, we have the ability to rotate as the functionality would dictate. So the main benefit here is that there is no post-processing assembly time required, and that you can pull this right off the bed and it's fully functional. Now, the downside, as you might be able to notice here, is that you must include tolerance for each of the parts to be able to print separately without fusing to its neighbor. Now, this is a lot more tolerance than is necessary for a part like this. As we can see, this moves a lot back and forth, but that just ensured that no parts are going to be fusing by the time that you pull it off the bed. Now, this is actually a good segue into in-situ embedding, which is another type of functional complexity. Now, in-situ embedding is when you take a printed part and hollow out a cavity inside of it that you wish to embed a component to be printed over during the printing process. So this requires you to design 3 parts. One is going to be the component to embed. Another is going to be the cavity that the part is going to fit into. And the third, which we'll discuss, is a shape converter. Now, I'll explain further in detail what that means, but in essence, this is going to compensate for any gaps that we might have between the cavity and the part that we're wishing to embed. So to paint this example for you, I'm going to put this piece of construction paper out, and this is going to represent our printed cavity that we're wishing to embed a part inside. So what we have is the layers going up with our Z direction pointed towards the top of the video, and our cavity that has been hollowed out right here in the middle. Now, note how I'm leaving the top as wide as the widest part of the cavity, just so that I can ensure that my part makes it all the way down in, and that there's no trouble getting our part in during the printing process. So up to this point, we've printed up to this layer, we have paused the printer, and now we are ready to drop in our component that we wish to embed. So we're going to take this, we can drop it down from the top, it's going to bottom out, and we're quickly going to notice that there are some very large gaps to the left and right of a part like this that would need to be compensated for, so that way the part doesn't move around. And as well, when the printer continues to print, if it tries to print over this gap, it might have some difficulty in filling in that void. So to compensate for this, we're going to implement what is known as a shape converter. And so I'm going to pull our embedded part back out. I'm going to grab these 2 yellow bits here, which are designed to fit around our embedded shape. And we're going to quickly notice that that's now taking the form of our cavity that we're wishing to fill. So as we bring this back down into the shape, we can see that we now have a nice flat surface across the top to resume printing, where the embedded part is going to be fully rigidly supported. So as we continue to print, we can see that our part is fully encased and fully embedded without the use of external assembly, adhesives, or any sort of binding agents necessary. Now, this is a very complex way of embedding a part, but it allows for a seamless transition where the outside of the part of the printed cavity, or the actual volume that you're printing in, is maintained, so you don't notice any seams because they're hidden by the layer lines, while you're still able to get the complexity of the internal part. So this has been a brief discussion on opportunistic design for additive manufacturing and the manufacturing technique known as in-situ embedding. I'd like to thank you, and hopefully I'll see you again.